Okay, 16.8 is all about Stokes theorem. The goal is to evaluate a line integral over a vector field using Stokes theorem. So what does it say? It says that the line integral with respect to the vector field, say f, so in symbols, integral over c f dot dr, that line integral with respect to the vector field is actually equal to a flux integral, believe it or not. Flux integral over a surface S, but the vector field in the flux integral is not f, it's the curl of f, dotted with the normal vector n ds. So a line integral with respect to a vector field f is equal to a double integral involving the curl of f, provided S is an oriented piecewise smooth surface bounded by C, the same curve C from the line integral, which has to be a piecewise smooth positively oriented closed curve. Also, f has to have continuous first partials in an open region containing S to ensure all of this works. Okay, let's examine some of this statement in green using a picture. So picture a surface S. Stokes' theorem requires that it has a rim on it. So this bottom curve at the edge of the surface is the rim. The rim has to be oriented counterclockwise. So the rim, this bottom edge of the surface, is what we're calling C from Stokes' theorem, and it has to be oriented counterclockwise, which means a little man or a little ant traversing the rim has the surface on his left. And then, of course, you have a normal vector. At any point on the surface, you have a normal vector oriented in some direction. We'll say oriented up. And in fact, we require the normal vector to point upward in this situation to consider this parameterization of the curve to be positive. And that's by convention. Let's look at some notes before I show you an example involving Stokes' theorem. Green's theorem is a special case of Stokes' theorem with S devolving into R and N devolving into K, the unit vector 0, 0, 1. To see this, just consider the right-hand side. On the right-hand side of Stokes' theorem, consider the integrand. That says the integrand is the curl of f dotted with n. But in this case, n is just k, so you get the curl of f dot k. But the curl of f is going to have, well, I don't care about the first two components because when you dot them with k, the vector 0, 0, 1, they're going to disappear. The third component is exactly the integrand of Green's theorem, dq dx, derivative of q with respect to x, minus the derivative of p with respect to y, where the vector field is given by PQR. And we're dotting that with the vector 0, 0, 1, that's k. So of course, you just get dq dx minus dp dy. Whoops. So yeah, Green's theorem is just a special case of Stokes' theorem. And the surface is just a region in the xy plane. Note number 2, for small c and s with a point P on S, f is approximately equal to f evaluated at P, and n is approximately equal to n evaluated at P. Both f and n, the vector field and the unit normal vector, change according to what point on the surface it's evaluated at. But if c and s are really small, then f is approximately going to equal f of p, which is a constant, as is n evaluated at the point P. So by Stokes' theorem, we can say that the integral over C of f dot dr is, well, approximately equal to the double integral over S, the surface integral over S, of the curl of f evaluated at P, the point P, dotted with the unit normal vector evaluated at P, ds. But since the curl of f evaluated at P is a constant, and n evaluated at P is a constant, we can pull out the integrand in front and say that this is the curl of f evaluated at P dotted with n evaluated at P times the integral, the surface integral, ds, 1 ds. Oh, but wait, this guy right here is just the surface area of S. So let's call it the area of S. And then we still have this stuff out in front. And on the left-hand side, I'll put ditto mark in the intermediate step. And then we still have the integral over C f dot dr. Now, before I give you an interpretation then of curl based on this statement, let's talk about the meaning of the integral f dot dr over C. Now we know we can think of this integral as work done by the vector field in pushing a particle along the boundary curve C. But there's another interpretation of this that's going to be helpful. Remember, we can think of this integral in terms of the unit tangent vector. We can think of this integral as measuring the circulation or flow of f around C. Now, this is because the bigger f dot t gets, the more in line f and t are. Remember that f dot t is equal to the magnitude of f times the magnitude of t, which is just 1, times the cosine of the angle between them. And this is largest when theta is equal to 0, when the angle between f and t is 0. In other words, when they point in the same direction. And by the way, that works approximately as well. The closer theta is to 0, the closer f and t are to pointing in the same direction, then the larger f dot t will be. So think about it. The larger this integrand is, the more circulation we have, or flow we have, of f around the boundary curve C. So that leads me to note number 3. If we can think of the left-hand side of this statement as circulation of f around C, or just circulation for short, then we can take this equation and solve for the curl of f evaluated at P dot n evaluated at P. We can do that by dividing both sides by the area of S. And then we get that the curl of f evaluated at P dot n evaluated at P is the circulation divided by the area of S. Or, if I switch sides, then we can think of the curl of f dotted with n as equaling the circulation per unit area, which we can also think of as rate of circulation of f around the boundary curve C. And Stokes' theorem says that adding up the curling of f on S, that's this part, Stokes' theorem says that's the same as the circulation of f around the boundary curve C. That's this part. So we can think of the curl of f as helping us to measure how much the vector field is rotating in the vicinity of that surface. And that leads to note number 5. If the curl of f equals 0 throughout the domain of f, then f is called irrotational and conservative, of course. Note number 6. For a given boundary curve C of S, the flux integral curl of f dot n ds is independent of S. Why? Well, again, Stokes' theorem tells us that this flux integral is equal to a line integral over the boundary curve C f dot dr. And of course, the surface doesn't enter into play when evaluating this line integral. This means that if C bounds, say, a flat region in the xy plane, or maybe C bounds some other surface, we call this surface S2 and the flat surface S1. What Stokes' theorem says is the integral of the curl of f dot n ds is the same over S1 and S2 or any other reasonably well-behaved surface as long as the boundary curve C remains the same. So these integrals, the integral over S1 is going to be equal to the integral over S2. So in this example, f is equal to the vector field with components y, z, and negative xy. S is the surface z equals 4 minus x minus 2y in the first octant. Let C be the curve created when S intersects the coordinate planes, and you're asked to find the line integral over C of f dot dr. So the line integral with respect to the vector field f. So I want to draw the curve C for you to show you how you would not want to do this problem. So we take this surface S. So S is given by z equals 4 minus x minus 2y. But probably an easier way to write it would be to write x, the x term, the y term, and the z on the same side. So I'd get x plus 2y plus z equals 4 if I bring the minus x and the minus 2y to the other side. Does everybody agree with that? Now I want to graph this thing for you. For one reason, it'll be a good review, and for another reason, you'll see why there's a certain way you don't want to evaluate this thing. So let's say this is the positive x-axis, positive y, positive z. Then what kind of object does z equals 4 minus x minus 2y graph to be? It's a plane. It's a plane. And if we only want to graph it in the first octant, we can graph the intercepts and connect the dots. Okay? So what would the x-intercept be? You'd have to plug in 0 for y and z. What would the x-intercept be? 4. So I'm going to go out 1, 2, 3, 4 and plot this point here. What would the z-intercept be? It would also be 4. And the y-intercept would be, if you plug in x for equals 0 is equals 0, you get the y-intercept. What would you get for that? 2. So go out 2 on the y. And then connect the dots. And then the plane is actually the interior of that triangle in space that I just drew, right? But C, the boundary curve C is the union of these sides of the triangle that we've drawn. the intersection of the plane. You get 3 intersections of the given plane with the coordinate planes, and that's C. And it's comprised of 3 piecewise smooth lines, right? You could consider the line in the xy plane C1, the line in the xz plane maybe C2, and the line in the yz plane C3. It's going to have an upward orientation. If you're not told, it's going to have an upward orientation, which means it has to be traversed, looking down on it, it has to be traversed in a counterclockwise fashion, like so, and then the normal vector would point out like that. Okay? So C then would be the union, this curve C would be the union of C1, C2, and C3. So that if we wanted to evaluate straight up the line integral over C of f dot dr, what would we have to do? What would that equal? Yep, it would be the flux integral over C1 plus the flux integral over C2 plus the flux integral over C3. You get to triple your fun, right? 3 problems in 1. But there's another way. If you consider C, the union of C1, C2, and C3, the boundary of this surface, the plane being the surface, the slanted plane being the surface, so if you consider this plane as S, then you could use Stokes theorem to evaluate this in one double integral, surface integral, right? Technically, it's a flux integral. So that's what we're going to do. It's going to be easier than evaluating 3 separate line integrals. By Stokes, this integral is equal to the double integral, well, flux integral is a better way to say it, over S of the curl of f dot n ds. One integral. And this will be easier. Okay? Now, look at the statement of the flux integral. It tells us what to do. What do we need? Work the integral from the inside out. What do you need to find first? The curl of f, right? So we need to find the curl of f. Let's work on that. The curl of f. Okay, well, okay, what does f say? Okay, so here's f again. The curl of f is equal to what? Well, we're going to use the pseudo-determinant to evaluate it, right? So this is a good review of finding curl. So across the top goes ijk. What do we put in the middle? Partials. The partials. d dx. The partial operators, right? They're not even numbers. It's like putting plus, minus, and divided by, the division symbol in there. So it's kind of an abusive notation. That's why it's not a real determinant. Well, it's not a real determinant also because of the ijk, but it's not a real cross product either. So d dx, d dy, d dz. And then across the bottom, what do we put? P, Q, and R, which would be y, z, and negative xy. So we take the curl of f. That's how we do it. So you cross out first column and ignore the top row and take, well, it's a pseudo-determinant of the remaining matrix, if you want to call it that. So you're not multiplying, you're taking derivatives, right? d dy of negative xy, let me erase that for the next step. So d dy, the derivative of negative xy with respect to y, what do you get? Negative x. So that's the I component, right? Because the curl of f is a vector. Okay, it's a vector field, right? Okay, and then, yeah.
Isn't it?
Oh, and then minus 1, yeah. Got ahead of myself there. So d dy of negative xy is negative x, and then d dz of z is 1, but you subtract that piece, don't you? So that's the I component. And then by definition, you have a minus here, cross out the middle column, d dx of negative xy, what does that get you? Negative y, because you're taking the derivative with respect to x, and then d dz of y, right? And that's the j component, isn't it? And then plus, what's the k component going to be? So cross out the last column and focus on this guy. So we get d dx of z, which is 0, minus d dy of y, which is 1. So we get minus 1. That's the k component, isn't it? So cleaning it up, I guess we get negative x minus 1i plus yj minus k. All right. Now, that's good. So we need that. And then let me go back up here for a second. What's the calculation formula that we use for any flux integral? It's the curl of f, we have to find that, dotted with, remember it's plus or minus del g, del capital G is what I gave you last time. In this case, dA. And in this case, it will be plus. Okay, so that means we've computed the curl of f, we need to compute del g. But first we need to figure out what g is. Well, we consider this guy, even though I called it f before, in the past we've called it g, right? So what is capital G? So capital G of x, y, z is what you get when you basically set z or set g equal to 0. Let me back off that statement. When you take your expression for little g and set it equal to 0, then the non-zero side you set that equal to capital G. Okay? So what is that going to be? If we want to keep the k component of del g positive, we need to keep z positive. So that means we'll bring this stuff to the other side and get z plus x plus 2y, and then bring over the minus 4. Okay? And then from that, we can go ahead and calculate the del g. What is the del g? What is del g, I should say? So remember, partial with respect to x, that's the first component. Partial with respect to y, second component. Partial of g, big G, with respect to z is the third component. So what do we get? Just... No. Just 1i, right? Take the derivative with respect to x, you get 1. So 1i plus 2j, right? Derivative with respect to y is 2, plus k. The derivative with respect to z is just this 1 right here. And put these right next to each other. Because what do we need to do with curl of f and then del g? Take the dot product. Okay, so we take the dot product, the curl of f, and we dot it with del g, and we get, okay, well, what? Negative x minus 1? What's the next piece of it? So this guy this guy times this guy, and then this guy times this guy. So what's that? Plus 2y? And then minus 1. So we get negative x plus 2y minus 2. That's our integrand. Now, we have to figure out what our region of integration is. Go back to the picture. Remember, it becomes just a double integral over r, where r is in the xy plane in this case. So, and how do you figure out r? Well, you project your solid region, which would be, well, okay, it's technically it's not a region here. You just project your surface straight down onto the xy plane, the region of integration. And it becomes the interior of the triangle defined by part of the x-axis, part of the y-axis, and C1, doesn't it? It becomes that region right there in the xy plane. Does everybody see what I'm talking about? So let me draw that separately. So that is, I think we went out 2 on the y, is that correct? Yeah, 2 on the y and 4 on the x. This guy is C1. We're concentrating on our region R, which is this region. Okay? So it would be best to express C1 in terms of a function of y and x, or with the input being x. So it's a line, right? It's the equation of a line. What is that line that C1 represents? Well, what's the y-intercept? Looks like 0, 2, or just 2. What's the slope? Looks like you go, you rise -2 and you run over 4. So -1/2, -2/4, -1/2 x. So the equation of that line is y equals -1/2 x plus 2. And if we want to set up our integral, then you could set up a little representative. Let me draw this a little bigger for you. You could set up a little representative rectangle to help you set up what becomes just a double integral, right? Double iterated integral. So our integral becomes something that looks like this, right? We'll go with the usual dy dx differential order, which corresponds to vertical rectangles. What does y run from? What's the bottom of what gives you the bottom of this rectangle no matter where you draw it? 0. And what does it end at? What is the top value on y? It changes depending on your input, but it's going to be given by the function -1/2 x plus 2. And then what does x run from over the entire region? 0 to 4. And there's some fractions involved in this, but it's a reasonably straightforward integral to evaluate. So I'm just gonna give you the answer on it. You get -8